In the past couple of sessions, we've introduced multivariate regressions as a potential solution to omitted variables bias. In this short example, we're going to look at a multivariate regression where we've got the natural log of average hourly earnings as our dependent variable and two explanatory variables. The first explanatory variable is a dummy variable for if the individual has ever been married or not. In other words, it takes the value 1 if they've ever been married, and it takes the value 0 if they've never been married. The second explanatory variable is the individual's age. Now, I've placed the regression specification up on the screen. In interpreting the coefficient, the beta 1 hat that we get is the estimated impact of an individual ever having been married, having controlled for their age. So in other words, for a fixed age, what is the impact on the natural log of average hourly earnings of ever having been married? Similarly, the beta 2 hat is the estimated marginal impact of an extra year of age, having controlled for the individual's marital status, having controlled for whether or not they've ever been married or not. So in other words, it's the marginal impact of an extra year of age holding their marital status fixed. So let's explore these regression results in a bit more detail. In this example, we're once again using data from the UK Labour Force Survey, and we're going to try and address the question about whether or not ever having been married has an impact on earnings. So let's start with specification 1, which just runs a regression of the natural log of average hourly earnings against the dummy variable for whether or not an individual has ever been married. The variable takes the value 1 if they've ever been married, 0 otherwise. Now, let's start by trying to interpret the regression results. The R squared here is 0.0231, which means that only 2.31% of the variation of the log of average hourly earnings is explained by variation in that married variable. So in our model, we're explaining 2.31% of the variation in our dependent variable, which is the natural log of average hourly earnings, by our model, and here the model's variation is determined by variation in that married variable. Now let's move on to try and test the statistical significance of the estimated coefficients. Our null hypothesis is that beta 1 is equal to 0 against the alternative that beta 1 is non-zero. We construct a t-statistic in the normal way. Our t-statistic is just beta 1 hat minus the expected value of beta 1 hat given that the null hypothesis is true, divided through by the estimated standard error of beta 1 hat. Now our estimated beta 1 hat is 0.153. Our estimated standard error is 0.027, so our t-statistic is 0.153 minus 0. Effectively, we just substitute in the hypothesized value, divided through by 0.027, which gives us a t-statistic equal to 5.67. Now, we'd need to compare this with the critical value from the t-distribution. Here, the number of degrees of freedom is, as always, the number of observations minus the number of coefficients that we've estimated. We've got 1,404 observations here. We're estimating two coefficients, a beta 0 and a beta 1. So we're going to have 1,404 minus 2 degrees of freedom, which is equal to 1,402 degrees of freedom. Now, if you were to look up the critical value in the t-distribution, you'd see that there isn't a critical value related to 1,402 degrees of freedom. We've already converged to the normal distribution, so the critical value is just going to be equal to 1.96 at the 5% significance level. Now, because our test statistic, which is, remember, 5.67, because the magnitude of that is larger than 1.96, we're able to reject the null hypothesis in favour of the alternative. That is that at the 5% significance level, we've rejected the null that married variable, being married ever, has no impact on log of average hourly earnings. Now, our estimated coefficient here is beta 1 hat is equal to 0.153. Because we've got a natural log on the left-hand side and we've got a dummy variable on the right-hand side, we can interpret that beta 1 hat as meaning that For individuals who have ever been married, they earn 15.3% more than those who have never been married. So let's just repeat that. The beta 1 hat is 0.153. The explanatory variable is a dummy variable. We can interpret this, because it's a semi-log specification, because we've got a log on the left-hand side, the impact of, or those who have ever been married earn 15.3% more than those who have never been married. Now let's move on to looking at specification 2. And the first thing that we note in specification 2 is that there is a big change in the estimated coefficient on married. There's a change from 0.153 to 0.078. So when we included just married in our regression specification, we had a coefficient estimated of 0.153. When we've introduced age as a second control, our new estimated impact is 0.078. There's a big change in our estimated coefficients, and the change is more than 2 times the standard error on that beta 1 hat. So that suggests that when we omitted age, we were suffering from omitted variables bias. So in other words, age may well have been a key determinant of the natural log of average hourly earnings that is correlated with our explanatory variable married. So in specification 1, we've omitted age as an explanatory variable. However, it may be that the true data generating process is that the natural log of average hourly earnings is equal to beta 0 plus beta 1 times by married plus beta 2 times by age plus an error term. And if that's the case, then we can show that in the specification 1, the probability limit of beta 1 hat is equal to beta 1 plus beta 2 times by the covariance between age and married divided through by the variance of married. Now, it's highly likely that the covariance between age and married is going to be positive. The reason is that when you're very young, you've not had chance to get married. As you get older, you have more opportunity to get married. So we'd expect, on average, those individuals who have ever been married to be older on average than those who have never been married. Similarly, we'd expect that as you grow older, your earnings increase simply because you gain more experience on the job, you gain more seniority, you gain more higher wages, and you gain higher average hourly earnings. So we'd expect both beta 2 to be positive, and we'd expect the covariance between age and married to be positive. So we'd expect by omitting age to get positive omitted variables bias. And that's exactly what we've seen. When we omitted age, we got an estimated coefficient of 0.153. When we've included age, our coefficient has got smaller, it's got less positive. It's reduced from 0.153 to 0.078. So when we omitted age, we had positive omitted variables bias, and by introducing age, we've lowered our coefficient from 0.153 to 0.078. We've made it less positive in specification 1, where we only controlled for whether or not an individual had ever been married or not. We got positive omitted variables bias on our estimated beta 1 hat. So now let's go on and interpret the results of specification 2. As with specification 1, if you're doing this in an exam, I'd also recommend that you look at the statistical significance of the intercept, but let's do it just for the slope parameters. So we're going to test the null hypothesis that, first of all, beta 1 is equal to 0 against the alternative that it's non-zero. We construct the t-statistic in the normal way, beta 1 hat minus the expected value of beta 1 hat, conditional on the null hypothesis being true, divided by the estimated standard error. Our t-statistic is 0.078 minus 0 divided by 0.028, which gives us a t-statistic equal to 2.786. Here we're now estimating 3 coefficients, so our degrees of freedom is the number of observations minus the number of coefficients that we estimate, so it's going to be 1,404 minus 3 this time, so 1,401 degrees of freedom. Our critical value is still going to be equal to 1.96 at the 5% significance level, simply because with a large number of degrees of freedom, remember the t-distribution has converged to the normal distribution, and the critical values from the t-distribution are the same as the critical values from the normal distribution. So the critical value at the 5% significance level is going to be equal to 1.96. Because our test statistic, which is 2.786 here, is larger than the critical value, we reject the null hypothesis in favour of the alternative. We reject the null that ever having been married has no impact on the natural log of average hourly earnings. We can do the same with beta 2. We test the null hypothesis that beta 2 is equal to 0 against the alternative that it's non-zero. We construct our t-statistic in exactly the same way. It's just equal to beta 2 hat minus the expected value of beta 2 hat, given that the null hypothesis is true, divided through by the estimated standard error, which is just equal to 0.015 minus 0 divided by 0.002, which gives us a t-statistic equal to 7.5. Again, this is a lot larger than our critical value, therefore we reject the null at the 5% significance level. Finally, we need to interpret the size of the coefficients. In specification 2, beta 1 hat, the coefficient on married was 0.078. This means that if we increase that married variable by 1, so in other words, we go from someone who's never been married to someone who has been married, the impact is to increase average hourly earnings by 7.8%. Because this is a semi-log specification, the coefficient is a proportional change in the dependent variable average hourly earnings. So someone who's been married earns 7.8% more than someone who has never been married, having controlled for age. So for a given age, someone who's been married earns 7.8% more than someone who has never been married. Similarly, our beta 2 hat being 0.015, this means that for 1 extra year of age, we're gaining 1.5% extra average hourly earnings. Now, the key message from this exercise is that in specification 1, we only controlled for if someone was ever married or not. Now, what we're almost certainly suffering from there is a case of omitted variables bias. People who have been married tend to be people who are older, simply because when they're young, they've not had the chance to get married. So on average, those people who are getting married are older than those who are not getting married, or have never been married, I should say. So what that means is that when we ran our specification 1, our coefficients were biased simply because the coefficient on married was picking up the fact that those individuals who were married were also likely to be older. We're seeing a significant positive impact of age on average hourly earnings. So when we omitted age, because age is correlated with that married variable, we ended up with bias.